the PowerPoint screen.
Oh, I just need to. Okay, I will not start with the PowerPoint. I will start with the first 5 minutes of my video because this explains with the animation everything the best way, and then when I go into detail, I will talk. Okay.
Okay. Yeah.
So now you see the YouTube video on the screen.
Yeah, it is good to see.
Okay.
And then you a good option is present the video in full screen. Okay.
Yes, of course.
When you go to present it.
Yeah.
And then maybe when you be preparing to present the video in full screen, maybe you will be starting and you will be doing your presentation.
Yeah.
Introduce yourself, and maybe when you show the YouTube screen, and then maybe you'll be starting Eduardo will be start to record. Okay.
Okay. Okay. It's 2:00 now. In your time, I don't know what. Anyway. So it's time. Are you all ready? So we can start now?
Yeah.
Okay. So first I introduce myself. I'm Thomas. My name is Thomas Herzig. I'm an architect. I live in Austria, in Vienna. Usually I'm involved in design of inflatable structures. So since 2 years, I'm also involved in the design of a Mars habitat because 2 years ago, astrophysicist from Hungary, Gabor, he asked me how about making a Mars habitat, and I was very fascinated about that idea. So even when there was no commercial background in the beginning, I was very much excited about it. I had some ideas of the concept, so I just went on with it, and so far, yeah, you will see the presentation now. So yeah. Let's start with 3 minutes of the video and then I will switch back to the camera mode. Do you have the sound?
Yes, it has the sound.
Okay.
Okay, here my wave stop. So I will explain just briefly about the conditions on Mars. Many of you might already know, but I think it makes sense just to repeat it. So Mars is a lot, you see the screen?
Yes.
Okay, so Mars is a lot smaller, of course. It has only about 38% of the gravitation. With about 100 times the cosmic radiation dose that we have on Earth because it has no magnetic field and it has only a very thin atmosphere that could stop radiation and also micrometeorites. The good thing is that the spin period is almost the same as on Earth, like 1 day on Mars is 24.37 hours, so it's almost the same. And one there, the actual tilt of the Mars is also almost the same as on Earth. It's 25 degrees, where there's 23 degrees on Earth. So also on Mars we have 4 seasons, but much colder, and one Mars year takes 687 days, so the year is twice as long. Because it's so cold on Mars, of course, for me it makes more sense to make a habitat on the equator, because on the equator at least sometimes you can get a temperature of 20 degrees, and yeah, so I continue now with the video. Wait. Yeah, there's a less. Yeah. So the difference to most presented concept of Mars habitat is that here we don't need any 3D printing. I think the reason why so many other teams are based their designs on 3D printing is because they have no imagination about the real air pressure for breathable air. In our atmospheric conditions, sorry, my cat, the air pressure has a force of 10 metric tons per square meter, 100 kilonewton. So this is an extremely high force, and it easily can support any deposit of loose regolith. So it simply is not necessary to 3D print, sorry, to 3D print the structure of the, or to melt down the regolith, and it takes a lot of energy, the 3D print process. Then that energy simply is not available on Mars because sunlight is available, but only half as much as on Earth. And so any other energy source could only kill power reactors, but they just deliver like 10 kilowatts of electric energy. And each of these kilopower reactors weighs about 1,500 kilograms. So it's very difficult to get the required energy for big structural walls. And, sorry, my cat is always on the table. Yeah. Let me continue with the website. Yeah. You see the screen now? Can you hear me? I can't hear anything.
Yes, yeah,
Oh,
we were all on
okay,
mute.
now I can hear you. Okay. Okay, this here is again so it's very easy because the inflatable membrane is a very lightweight structure. It can easily be produced on Earth and it can be tested on Earth. While if you want to make a 3D printed structure on Mars, it has to be done fully automatic by robots, and it's very hard to control with the millions of kilometers distance we have on Earth. So when the crew arrives on Mars, they just can hope that everything has been done right. And with inflatable structure, we don't have these problems. They can take it in the spaceship, and even if some robots fail inflating them, it could be done by human power in a reasonable time. And also depositing on the roof is a lot easier and requires a lot less energy than 3D print. Yeah, here you see so design is in a way that the biggest part of the radiation is just absorbed by the deposit on the ceiling, but also from the sides. So only in very tiny angle radiation can enter into the greenhouse, but also only in the outer areas, in the inner areas where humans walk around. There's no cosmic radiation yet. So this is the design with the core for living space and the outer space for greenhouse. Yeah. And then you can just connect several greenhouse units to some kind of village. So you have like modules for large inflatable halls. You have these connecting tubes. And to gain the optimum of sunlight, of course, these greenhouse units all are oriented from east to west. So the sunlight in the equator comes from top, or it goes from north to south. Yeah. And all the traffic modules, they are double. So in case one connecting tube gets an air leak, it can be just closed and the rest of the structure is still active. So you can always bypass a broken tube. Yeah. This is like a concept for larger structures for meeting halls. And you see here, these are ropes that reinforce the structure. Because with inflatable structures, even under the same air pressure, the larger the structure is, the higher get the forces on the membrane, and there comes a point when you just need some ropes, and also the ropes give the right structure, because in between you have something like columns, but with negative tensile forces instead of compressive forces. Yeah, this would be like a whole village. This is a other connecting module that only contains like living rooms and bathrooms. And all the walls here, they are inflatable modules as well. You see here on the floor plan, like this kind of grid, it contains nylon zippers, and then you can just zip on the inflatable walls, but you also easily can change the position. And yeah, just want to say, like one of these greenhouse units that have a length of 50 meters and a width of 7 to 9 meters, they only weigh about 2,300 kilograms, everything. So it's very lightweight. So the payload is very little, and most of the weight just comes from the deposit from the Mars regolith. Yeah, you see, this is so also the deposit helps to reduce the forces that come from the inner air pressure, so it keeps it in a balance. Here's some example of inflatable structures I've done here on Earth. So this is similar to the inflatable wall elements. Here is a shower cabin just made of a thin transparent membrane, which would be that one. Or like furniture also, like one chair could only weighs 1 kilogram. And there's another version for the moon. Of course, the conditions on the moon are different because on the moon, not the equator would be the best place, but one of the poles. The reason is that one day on moon takes 14 days. So you would have a night time of 14 days without any sun energy, without any light. But on the poles, there are areas on high mountains or peaks of craters where you almost permanently have sunlight from a horizontal direction. And in the deep areas of the craters, you have frozen water. The problem with the water, it's the same as on Mars. If you have no atmosphere or a very low density atmosphere, water starts evaporating at 2 or 3 centigrade above zero. So there's no water on the surface of the moon or on the surface on the Mars, only maybe in caves or in areas where sunlight never comes, so it can stay frozen for all the time. And of course, water is a important resource. So on the moon, we would take the advantage to have the permanent sunlight, but frozen water as well. So the design is adapted and a little bit different. So here we see the sunlight comes horizontally, and we have an inflatable mirror that reflects the sunlight downwards vertically. And here we have a cone-shaped mirror that reflects the sunlight in the toroid greenhouse around. And everything, of course, is covered with regolith. Again, here you could even make a thicker deposit of regolith because the gravity is a lot lower. And this is a 3D picture of this. So in this case, in the center ring, there would be the greenhouse. In the outer ring, there would be the living space for the crew. And you can make tubes and connect this with another unit. This also is another option for an existing lava cave. So you just need to drill a tunnel here, and then the sunlight is focused and spread out again, and then you just make an inflatable structure inside the cave. The good thing about the vacuum on the moon is that you have no heat losses through transmission or convection. Only the radiation of heat is an issue. Yeah, so that's how the lava cave and the connection. And so let me switch to the okay. So my idea was, if that concept with greenhouse and living space works on Mars or Moon, it would be even easier to do it on Earth. And so we have greenhouse in maybe like in the desert or other environment with harsh conditions, and you could produce food there for still growing population. And so this is a derived version of the Mars habitat for Earth. So again, this would be in the mountains in Austria. You have the greenhouse area here, you have the deposit. Of course, radiation is not an issue, but the deposit helps to keep moderate temperatures in summer and winter. These are mirrors that reflect the sunlight also to the north side of the building. The problem with conventional greenhouses is, like you see here in this picture, they lose a lot of heat in winter and they get a lot of energy in summer in the daytime from the vertically arriving sunlight. That you don't answer. The problem is overheating in summer and the need of heating in winter. And you need a lot of resources to produce all the steel and aluminum and glass. Is an inflatable structure that uses a lot less resources, but of course still you have the problem with overheating inside in summer. Here, this picture, we see it's a so-called bottle garden. So this is the oldest, on this picture, this is the oldest so far known bottle garden in Great Britain. It's never been opened since 1972. So it's closed, you put in some soil, you put in some water and some seeds, and then the plant grows inside. And the water never gets lost because the water condensates on the surface and runs down again into the soil. And then some leaves decompose and they produce carbon dioxide. So the plants have carbon dioxide to produce oxygen through photosynthesis and build up the organic mass again. So it's a small closed ecological cycle that we want also to bigger scale in the greenhouse. Here you just, this picture demonstrates like when you have the ground, the deeper you go down into the ground, the temperature changes get less in the seasons. So the temperature gets closer to the annual average. Here you see temperature curves, sorry. This is the air temperature changing in summer and winter. And these are the temperature curves in certain depth of the ground. Or here you see it again. So the deeper you go into the ground, the flatter the diagram gets, and the peaks, the low peaks and the high peaks, they are a bit delayed. So the highest temperature is not in July, but maybe in September, and the lowest point is not in January, but in March or even April. And notice effects from wineries. So they are underground, so you always have cool temperature in summer, but it never gets too cold in winter. And this system has been used for thousands of years. So this is a very old housing in Turkey, in Cappadocia, from the 4th century before Christ. And here you see a more modern design of a building that uses solar energy, but also the mass of the earth. So the optimum is, of course, to make a glass wall that catches most of the sunlight in winter. Now I'm always talking about moderate climate. In Brazil, everything is different, of course. Yeah. And the mass of the soil, the ground protects, it keeps in the heat in winter, and so the problem to use that system for a greenhouse would be you would need a lot of steel and concrete to support the high weight of a deposit of soil on the ceiling, because you might have 1,000 to 2,000 kilograms per square meter, and no normal steel glass structure of a greenhouse could hold that weight. But with an inflatable structure, it's easy because the air pressure works against the weight, so you still only need a very thin membrane, and all the job to carry the high weight of the deposit is just done by air. Yeah, here we have the old picture of the Mars habitat because it's derived from there. So here's an example for an inflatable greenhouse in the desert. In desert, you especially can make use because in the nighttime, the temperature falls down considerably. So here we see again like a tube with the plants inside. The ceiling has a thick deposit of sand, and then you have, of course, the mass on the ground. And through the deposit and through the mass on the ground, we lay air pipes. So first, of course, when the sun is high at noon, all the sunlight is held back. And here we say some sections how it works. So this would be July in the daytime. So the sunlight is held back from the ceiling. I have to say, in the desert, in the daytime, you might have a light of about 100,000 to 150,000 lux. But most plants only need 15,000. It's a tenth of the total available sunlight. And when they get more sun, they just don't produce more organic mass through photosynthesis, or they even stop the process because it's too much light and too much heat. The diffuse light that comes from the side is enough. In the nighttime, the cold air of the night is blown through the pipes, because in the daytime we have 45 degrees, and in the nighttime the temperature drops to 25 degrees. So the mass of the deposit and the mass of the soil below is cooled down to 25 degrees, and in the daytime these cool masses of the ceiling and the ground will absorb the additional energy, the heat energy that comes from the sunlight, and of course through transmission through the inflatable wall. Yeah, on the right side you see the same in October. So the sun is a bit flatter, the temperature not as high anymore, but we still use the cold temperatures in the nighttime to cool down, because we just do everything to cool down the mass of the soil. Yeah, and this is January. So in January, sunlight is flatter. It's like in a 45-degree angle in the Sahara, like in Egypt or in Sudan. So now, and the outside temperature in the daytime is only 18 degrees. So the sunlight is welcome to enter through the side and produce a little bit more heat. And still we cool it in the nighttime, because when we cool the deposit in winter, we still have some reserve to absorb more heat in spring and summer. Yeah. Here again you see a section. So of course it would make sense to use this area for solar panels. It could be either photovoltaic panels or mirror that for thermal solar power station that reflect the light on one point in the tower. Here you see also, in the daytime the water evaporates and condensates on the ceiling, where it drops down again to the ground. Here we see an array of greenhouses in the desert, and you could even put them closer together if you have a mirror here, so the sunlight that comes from this side would reflect the sunlight to the north elevation of the greenhouse as well. Yeah, this is an example how it could be adapted in cold climate, for example, in Russia. So in this case, it doesn't make so much sense to open the north side, because you would lose a lot of heat and you wouldn't gain much sunlight. So only the south side is open, and we have extra mirrors to get more sunlight into the greenhouse. Yeah, and here the same system. So then we use the hot air that from inside, because when the sunlight gets in, it gets hot inside to heat up the soil around, and then we have a warmer environment for the winter. This is also area, of course. In this case, the distance needs to be wider. Or when you have in Europe a south slope, then of course it's more efficient. You can put them closer together. Here you see the annual temperature curve. So this is the temperature, the air temperature in the daytime in the desert, in the Sahara. So we have a peak of 45 degrees in summer, and the lowest point is 18 degrees in winter. And this is the this is the air temperature at nighttime. So you see there's a lot of difference, and we can make use of this difference. So the green line is still a lot flatter and lower temperature curve daytime in the greenhouse. So the temperature doesn't get higher than 35 degrees, which is the maximum for plants, because any temperature above, they will reduce photosynthesis. The air temperature curve in the nighttime. And here, and the black line is the soil underground, so this is the flattest curve, of course. And here's the example for Moscow. So it's pretty similar, but with on a lower level of temperature, of course. Yeah, so this would be like a big array of, and so now this year I will build a prototype in Austria, a small prototype. So of course I had to recalculate all the energy, the sunlight emissions, everything, especially for the conditions here in Austria. So we see something similar to the Russian version, but a bit more open to the vertical direction. So that part facing the north is all covered with earth, and this is the transparent part. So you have to carefully calculate, because if the part is too small, you don't receive enough light. But if it's too big, you easily overheat in summer, or you lose too much heat in winter, because of course the heat losses or the heat transmissions on the transparent membrane are a lot higher than through the soil. So this is the geometry in January or November. So the sunlight comes from a very flat angle. We want to maximize the sunlight, so we have additional mirrors here on top and on the bottom that add sunlight. And here around we have pipes, collector pipes. So when there's too much temperature inside, these collector pipes transfer the heat into deeper areas of the soil. Yeah, this is February and October, so the sun angle. This is much higher. So at this time, when we receive more sunlight, and we don't want that much sun, so the reflecting area gets smaller. And also the higher the angle is, the smaller the area of sunlight is. So we get the maximum in winter, and we reduce the sunlight emissions in summertime. Yeah, this is May and July. So here, like here, we only, and this is, So here in June, when the sunlight is on the highest point, so we only have 146 centimeters of projected area of sunlight that comes inside, while we have effectively 263 in winter, including the mirrors. Yeah, and so now this is the temperature diagram for Austria. So this is the sunlight that's available on 1 square meter of area free land in Austria. So it's the daily emissions are 6,000 watt hours per day in summer, and it goes down to 900 in winter. And the green line would be the ideal amount of sunlight from sunrise to sunset. Of course, you never get it because the sun is too low in the morning, and you have clouds, so you never get it. And so the red line is that what we really get according to the calculations. So in the summer, it's very close to the ideal line. In winter, we cannot get to the ideal line because there simply isn't that much sunlight. But we are a lot closer than what is the sunlight on the outside. And here are the temperature curves. So this hatched lines, this indicates the difference between night and day average. And the thick line is just the average of the daily average. So this is the blue line. This is the temperature curve of the soil around the greenhouse, and this is the curve which is just close to the greenhouse. So of course, there the temperature changes are higher. The green line is the air temperature inside the greenhouse. And the red line, that's the outside air temperature. So of course, it's in winter, we have a lot higher air temperature inside than outside, while in summer, it still is a bit higher in average, but not that much higher. The reason why it's high is simply because of the so-called greenhouse effect. When the sunlight enters a transparent membrane, so it absorbs the infrared radiation and it converts visible light into infrared radiation. So to balance and to avoid overheating, we need these collector pipes. So when the temperature goes above 30 centigrade, the water pump starts operating. Water is pumped to these pipes close to the wall of the greenhouse, and they pump the water in a second collector, which is deeper in the ground. And the deeper you go into ground, the closer the temperature is always at 10 centigrade. So it's like the layers of an onion. So the closer you go to the greenhouse, the warmer the soil gets. But that means also that you have, let's say, 30 degree here and you have 10 degree here. So the distance from the temperature difference also is the thickness of the heat insulation of the soil. And so what we need to do is we have to use the temperatures of the soil in a way to keep moderate temperatures inside. This is a 3D model of the whole thing. Now for the prototype is 10 meters long. So here you see the coils of the collector pipes around the greenhouse cylinder. And here this is the part of the coils which is in the deep soil where the heat should be transferred to. And here's the pump. And that part is the airlock because you need to keep it under higher air pressure. So we need an airlock for this structure. Yeah, this is just an example. You see, this is the kilolux of light, and you see when the light is low, the higher the light gets, the more photosynthesis the plants have, but only until a certain point, and then the curve flattens, so it doesn't make sense to receive all the sunlight. So at around 20,000 kilolux, it's more than enough. Only there are some other plants like corn, they still increase in the hot sun, but corn is not something that you usually would grow in a greenhouse. This is a even smaller prototype. It's just 2.5 meters long, just to test all the structural things. You see here some ropes to reinforce the structure, because that part which is underground, it's a white reinforced membrane with nylon fiber, but the transparent membrane does not have the same tensile strength. So you need these ropes, and so the membrane only needs to hold the air pressure which is within one mesh of the ropes. And so I made tests. I had to test if that kind of structure is really 100% airtight. If there's also an airtight nylon zipper to test if it can hold that high pressure. So I inflated it with 1/5 of our atmospheric pressure, which is then almost as hard as a car tire in this size. And yeah, so it could hold the pressure. So now I know when I make the big prototype which is 5 times as large, then it will work. Okay. Can you see me? No, wait. Wait. Can you see me now? Okay. Yeah. So if you have any questions.
Thomas, congratulations for your work. So very good content about sun energy. I think sun energy is the key to the future of our planet and also on others. My question is if you do this job on Austria too, or just planning for an habitation on Mars, because it is so great to see a project who utilizes the sun energy in that way with so much science, with so much technology, and congratulations for you.
Thank you. Well, I started with the Mars habitat, and then I just, like it's often like in space technology, you have to develop something for space, and then suddenly you find out that it's also, the technology also can have an application on Earth. And that was the same with the greenhouse. I thought, oh, yeah, maybe a greenhouse. And I have to say, I got a funding from the Austrian government for the greenhouse prototype now, so I can work on it. And the year before, I applied the same kind of funding for the Mars habitat, but they didn't give me the funding because they thought it's not useful and who cares about Mars. And so, but now there's more use on Earth. And but I don't forget the Mars part, so I hope once the greenhouse will be successful on Earth. And of course, when I test the prototype, all the experiences with the prototype here can be useful for.
Yeah, thank you.
Okay, you're welcome.
Hello again.
Hello.
Congratulations, and thank you for the sharing. Actually, I feel a little bit a familiarity here because I have a bachelor in civil engineering, and my thesis, it was on bioclimatic architecture about dowels on a volcanic area. So I found a lot of similarities. I have some questions as it is, if you have found or thought how we could solve the problem of transmission of the pipes of the excavator, and what exactly have you thought would be the material?
You're talking about here.
Mars.
Mars.
Here is more easier.
You mean the membrane material? You mean?
Yeah.
Yeah. Well, okay, that's another thing, because I know the materials that work on Earth, and I know also the issues we might have with the material on Earth. I mean, the biggest issue is always the UV light for membranes. So once it's underground, there's no problem with the UV light, but it's permanently exposed to moisture. On Mars, with the Mars regolith, the moisture is no problem because it's dry. But we have harder radiation and we have temperatures going down to -90. So for Mars, we would have to get into contact with the factories that produce these membrane materials and say, okay, can you make a test at -90 degrees? Will it still be feasible? We have to make tests. Will it still be UV resistance under the harder conditions on Mars? That's of course another step. I mean, I will not be able to, even when I get the funding from the Austrian government, I will not be able to solve all these problems because you need a lot higher budget to make a habitat on Mars work. But I think I know the way, which steps to undergo. And usually for now, so the material is, it's a TPU, it's thermoplastic polyurethane. So for the non-transparent part, the TPU is reinforced with polyamide fiber. So it has a very high tensile strength, and the transparent part is just pure TPU, but it's a so-called aliphatic TPU, which according to the supply is UV resistant. But also that needs to be proven over the years. If it's UV resistance just for 10 years or for 20 years or 50 years. And there are alternative materials too, but TPU is for now the option I want to go for. Yeah.
So we have to find the way.
Yeah, but if you like, I mean, maybe we can exchange contacts, because I would also be interested to see what you are doing with the inflatable structures. And
Yes, of course. Now this period I actually am on the space field. That's why I combine things.
yeah.
My master is in space science.
Mm-hmm.
So I'm at this period now.
Okay, good.
Congratulations, Thomas. I appreciated your presentation, and my imagination now is filled with these different ideas and applications for your work. I was struck by when you showed the picture of the prototype, and you inflated it with the ropes, and combined that image in my head with some of the temperature graphs and the daily changes, the diurnal nature of temperature swings on the different planets. And it got me thinking, is there or have you thought of a system inside the habitat or inside the greenhouse that will automatically account for those pressure changes inside the material because of its exposure to those great temperature ranges on the outside? I know that in Biosphere 2 in Arizona, which is a very, very large greenhouse setup, they need an inflatable or adjustable, what they call lung, because during the day all that air is under such great pressure it needs to go somewhere. Yeah. So they created a space for that air to go so it doesn't blow out the glass. Is there a checks and balances system inside the material so that it doesn't happen?
Okay, I have to go deeper in the thing. The Biosphere 2, they had no considerable overpressure. They had almost the same atmospheric pressure, and the glass structure would only be able to take a little overpressure. As I told you, atmospheric pressure is 10 metric tons per square meter. So even if you have a difference of just 1%, that already means 100 kilogram on 1 square meter. So this would be probably the limit the glass structure could take. But on the Mars habitat, I mean, we work with atmospheric, or at least half atmospheric pressure. That means on a 4,000 meter high mountain. So this would still be breathable air, and we would just increase the from 21 maybe to 30%, and it works fine. But still, it's very high force. So if you just increase the pressure by 1%, that's nothing for the structure. In the greenhouse prototype I will build in Vienna now, there's a pressure switch and a side channel blower that will always uphold the pressure. Little losses will not be avoidable because the pipe from the blower to the inflatable greenhouse, it has a non-return flap, but that just works on gravity, so there are slightly air losses anyway. So it will, probably the air pump will need to operate twice a day for a few seconds. And the Mars, I mean, I think it's if the temperature, I mean, first you could make some extra inflatable structure just to I think the difference of 1 or 2% doesn't make any difference for the structure, because you need that reserve anyway. I mean, let's say if you say it needs to take let's say 500 millibar of pressure, then the structure must be designed for taking twice or 3 times as much to have a safety.
That makes sense. Thank you very much.
You're welcome.
You listen me?
I hear you, yes.
Okay. Congratulations, Thomas, for the presentation. Unfortunately, I have lost the audio in the first minutes, and maybe I lost some information related specifically for the mass habitat. And I want to ask you if the model that you have for the Moonbase inside of lava tubes, is it possible to do something like that on Mars, or it's better the model with on the Mars surface that you have proposed? It changed some.
The reason why the design is different is the sunlight that we want to use comes from a different angle. So because the moon is in almost in the same orbit as Earth, so the moon receives even more sunlight than Earth because there's no atmosphere, no clouds. So it's no problem just to go on one of the poles and just horizontally reflect the sunlight. And the poles are the better place because water is available there. On the Mars, for the availability of water, also the poles would be better, but it's too cold and we simply don't have enough water. So from the sunlight, again, it makes more sense to go to the equator. And so that's why I made a concept where the sun recently I got more detailed information about the temperature and the sunlight on Mars. So what I found out is that even when they have these dust storms, you still have 30% of light because the ambient light is so much. So the dust has a less effect than clouds here on Earth. So that's a good point. And the deposit of the regolith has a very low heat transmission. So in general, what I found out is now the issue is not so much to gain as much sunlight as possible and to avoid heat losses. So we will more have the problem, even on Mars, that we have too much heat inside. And so it would be possible, I think. It doesn't necessarily to be on the equator. We could make it on the 30s, 40s latitude on Mars, maybe too, but that needs a different design. So that's why also the design for that is different than the design for Austria, for Russia. You always have to carefully get all climate data. So I got the temperature data for Austria, the monthly average temperature, the daytime, nighttime, and I got all the sun emissions for, let's say, a horizontal, a vertical, and the declined square area. And with this data, I made a calculation. So it's an Excel sheet which contains all these data, and you need to consider the storage of the temperature in this mass of the soil. And so the principle is the same. You have an inflatable structure covered with soil, and you might need mirrors or not, so to keep out the radiation on Mars. And but you need an individual design.
Thank you, and it's also good to know that you have received funding to do your with the greenhouse. It's really awesome.
Maybe next year I get a better funding. I can do it in the Sahara.
Great.
I have one more question about the moon. On the moon, we have the problem of the material soil, which is like a glass.
You mean the regolith?
No, on the moon, it's not actually regular. It's
the particles. The particles.
Yes. The particle is like a glass.
Yeah.
And this is a problem even for astronauts.
You mean they could cut punctured?
Yes, exactly. Also, NASA has made a lot of challenges.
Well, the problem also is on Mars because they have not that much wind. In our desert on the beach, the sand is always in movement. And on the moon, the sand and the stones are very sharp. So I would just make a layer of like a filth layer over the membrane, just a protecting layer. And or what we also could do, it's like you have a machine where, well, you know, like these machines we have here to mix concrete. So you put in the sand and it always rotates, so all these little particles get round after a while. And then this is the first layer you put over the membrane, and the sharper parts on the outer layers that don't get into contact with the membrane.
Okay, got it. Okay, thank you.
Yes, do you have questions, Eduardo, comments?
Yes. Well, we need a balance. You know, it's a closed ecological cycle. So inside, now I talk about Mars and then I refer to the greenhouse on Earth. Okay, so in the Mars or Moon, the plants inside, they should, of course, they should produce enough oxygen for the humans inside to breathe, but not only for humans. You also have bacteria that decompose the organic matter of the plants or that decompose the excrements of the humans that all need to be collected, of course, because nothing must get lost there. And you have insects there for the pollination, like bumblebees or whatever. I mean, that's a really complicated field because what we just naturally have on Earth, I mean, if you build a greenhouse on Earth, it's not a complete ecological cycle. It's just one part, but you still get the air from outside, or still insects can come in from outside, or you bring fertilizer in. But on the Mars habitat, everything needs to be in a balance. So, and that was the problem also in bioatmosphere too, because the oxygen level went lower and lower, because probably the reason was so they produced more carbon dioxide and other stuff through decomposition than they could produce oxygen through photosynthesis. Well, this needs to be, of course, we need experiments, we need a lot of input of biologists who know about these things better. And for my Earth prototype now, I mean, I will also see, but the main issue here is not to have enough oxygen. The main issue is to have enough carbon dioxide, because humans will just rarely enter the greenhouse. So the problem is, once the plants have used up all the carbon dioxide, where does extra carbon dioxide come from too? So the only possibility is just to blow in new air, what I want to avoid, because I don't want the air pressure run all the time. So I will need one area of for decomposition of all the organic matter. So everything that grows and is not eaten, like when you have the leaves and the twigs, that needs to be decomposed inside the greenhouse. I have insects inside for the pollination, and that should be in a balance. On Mars, that issue is not a problem, because you have a lot of carbon dioxide in the atmosphere, so you just need to add carbon dioxide from outside if you don't have enough. But here in the greenhouse, it needs to be in a balance. And let me just add, because nowadays in the professional agriculture, like they have these high-tech greenhouses in Holland, they even blow in extra carbon dioxide to increase the growth of the plants. So sometimes the greenhouse is connected with a factory and they use the exhaust from the factory, or they they buy tanks and blow it inside the greenhouse. But all the thing, you know, they have LED light inside. They have to heat the greenhouse in winter. They have hydroculture plants, so that the plants don't grow on soil. So that means they have to add all the fertilizer, everything, all the nutrition for the plants. They have to add to the water because the plants just grow on rock wool. So it's not the ecological cycle, because how can you decompose organic waste and use it for that kind of high tech? So I've read some reports that in a European high tech greenhouse, if you harvest one tomato, it needs 200 milliliters of gasoline. So it doesn't make so. So it's also, when we make a greenhouse working on Mars, we can learn a lot how to do this thing, because we simply don't have. So we'll learn how to make it sustainable too, because we have no other chance than having a sustainable greenhouse on Mars. You're welcome.
Thomas, did I hear you correctly in saying that you, in your prototypes and in your thinking, you would actually prefer conventional agriculture over hydroponics? Is that right?
I personally do, but I'm not a specialist. I'm in contact now with two professors from the University of Agriculture. I mean, both systems would work in that greenhouse, but I prefer the natural way. Yes. But of course, it needs to be evaluated. Maybe at the moment, it's a if I have the greenhouse in my private garden, of course, I would always go the natural way. If you say an investor, you need to make money with it, then you also need to have options and see and compare, because it doesn't work commercially if the tomatoes from my greenhouse are 3 times as expensive, and there's a lot of price pressure on any agricultural product. But it's not the real price, because the nature, the price it's paid that our energy that comes from fossils is still too cheap. But it's from the financial point, it needs to work too.
Yeah, good insight on the pros and cons. Yeah, thank you.
You're welcome.
Okay, Thomas, I'd like to thank you about your presentation. It's good to know that you get fun to develop your research, because it's very hard to develop these activities without financial support. And then if you would like to do next steps or develop or more research, we need more funding for that. No, yeah. It's very important. I don't know if it's possible you get European Space Agency, or if it will be possible receive some support to them. But I believe it's very important, because it's a very good steps that you're doing, but I believe you need more support.
Yeah. I hope I will get it. It's not easy, because like for small countries like Austria, they like there's an ESA program, but so each country pays something into the pot for the funding, but each country wants to get out the same money. And for Austria, usually they only fund projects which are not involved into manned space missions, because Austria doesn't send. So nobody fund companies who let's build some components for satellites, but a Mars mission is a manned mission, and that's why it's very hard to get the funding from that. So because I already called the person from the FFG Foundation who cooperates with ESA, and they said, oh, well, you have no chance with that project. But maybe there are other ways.
Yes, I hope. Yes, I'd like to know if everybody have more questions, or we would be finishing.
Yeah. No, I go with the greenhouse now here, and I will use all the experiences I make for the Mars project too. And maybe when I can demonstrate the prototype here, it's more convincible for investors of organizations to do funding, so even for a Mars mission. Then,
Yeah. Yes. And more questions? Yes. Yes. I'd like also to thank James. Be watching the presentation, and also you're doing something interesting that I had commented yesterday with David at these missions. Had been a very good opportunity to connect different people and also exchange a lot of ideas and see some opportunities or some perspectives of cooperation between some members, and we had saw a lot of opportunities that was provided from the participation of from the moment that we have members participating in the missions, and then some things are happening after the missions, and then this is a very good perspective, I believe.
Mm-hmm. Yeah.
Yeah. Okay. Today is also a very important day because we had the launching of SpaceX capsule. No, and then we are very interested to see. And then I saw some images from the coast of Florida. I saw some clouds today. They start a little cloudy in one of the areas of Florida coast, but we hope that during the day it will be a sunny day, to the day to the launch. Yes, a lot of people around the world waiting for the launch,
Yeah.
Okay, guys. In this case, thanks so much.
Thank you.
Thomas,
when is the next presentation? When is the next presentation?
Yeah, tomorrow we have the presentation of 3 members of the team. Margarita will be doing a presentation about the sanitation center. Victor will be presenting the health center, and also Eduardo will be talking about engineering center, and then how these facilities would be, what are the content, what are the functionalities of each specific infrastructure in a possible space habitat in Mars and Moon, and also and this is the content for tomorrow. And Friday we'll be trying to see do a discussion how our discussion will be more aligned to propose something to SpaceX, and also we will try to find some documents related to the SpaceX future plans for Mars and Moon, and then we are doing a broad discussion about this, how the presentations will be doing a contribution to Mars and Moon habitats.
Good.
Yeah. Okay, and then James and Thomas are invited to be with us if have time. We're supposed to be the same time, okay?
Yes.
In the same link. Okay.
Yeah.
Thank you for the invitation. I appreciate it.
Yeah, I appreciate it too. Thanks a lot, and I will be at the next presentation too. Yeah.
Okay, in this case, have a wonderful day, and then you'll be contacting also during the time of the launching, or maybe some minutes before the launching. Maybe you'll be using a channel or the WhatsApp group, or maybe this video room. To be commenting or doing some discussion about the launching, maybe. Okay. Okay. Have a good day.
We'll be watching that on NASA TV on my phone. NASA has an app that is a NASA TV channel, and it is a free app, and you can watch it live on your phone from NASA headquarters and all of their programming. So if you are interested, you can maybe have that going on as well. My family and I will be watching that later this afternoon. Maybe we'll get a picture and post it on social media.
Okay. Yeah, very good. Yes. Okay. Thanks so much. I did also some print screen from the audience today, and then I'll be sharing with you, okay? With everybody.
Okay, thank you. Yeah.
Okay. Have a wonderful day. See you later. Okay, thanks.
Thank you.
Bye, everyone.
Bye. Bye-bye. Thanks.
Bye. Thank you very much.